Hello, colleagues and friends. My name is Lantao Xing, and I'm a Presidential Postdoctoral Fellow from NTU, Singapore. Today, I'm very happy to give you a brief introduction of my research topic, that's event-triggered control from theory to applications. We know that event-triggered control has been widely investigated for networked control systems. However, the application of event-triggered control has been rarely reported. In this video, I'm going to provide two examples about the application of event-triggered control. Okay, the first example is event-triggered control for batteries. And in this work, we propose a new DAC algorithm, and we'll apply this new algorithm to the control of batteries. And this result is published in Transactions on Control of Network Systems. Okay, first, the new algorithm. The traditional DAC algorithm in reference to, it is dependent on the initial conditions, so it's not robust against communication link failures. And we make some modification about the traditional algorithm and propose a new one, the lower one. And this algorithm is independent of the initial conditions, so it is robust against communication link failures. And apply the designed algorithm to the control of these battery systems. And we have two objectives here. First, fulfill the overall power command. This means the output of all the batteries should meet this reference value. The second is the SOC, the state of charge of all batteries should converge instead of diverge. And we use the real-time simulator to test our algorithm, as can be seen from this figure. Even when the communication link failure occurs, our algorithm can still guarantee the desired performance. And more importantly, with the event triggering mechanism, the number of signal transmissions for each battery could be reduced from 60,000 to 15,000. That's a reduction of almost 75%. The second example is event-triggered control for DC microgrid. And in this work, we propose a new distributed secondary controller for DC microgrid. And we extend the result to the event-triggered control, and this work is published in Transactions on Smart Grid. This is the problem formulation. We have a number of DC-DC converters which are connected parallel to a DC bus. And we have two control objectives. The first is current sharing. The other one is voltage restoration. And we propose a new secondary controller. And first, we identify a new parameter. We name it as virtual voltage drop. And based on this new parameter, we design a new distributed secondary controller. And we can show that this controller can guarantee both current sharing and voltage restoration. And this is the experimental result. And this experimental system is in our lab. And as can be seen here, our algorithm can cope with both resistive load and the constant power load. Then we extend the above algorithm to the event-triggered control framework. And we design an event condition here. And this is a controller. And again, we can show that this new controller, this event-triggered controller, can also guarantee the control objectives. And this is the experimental result. As can be seen here, it can cope with both resistive load and the constant power load again. And more importantly, the event-triggered mechanism reduces the number of signal transmissions for each converter from 480 to 158. That's a reduction of almost 67%. This is our research team. It's a very dynamic and very productive team. I want to thank everyone here for your support. Let's keep up with the good work. Thanks for your attention and hope to hear your feedback. Thanks.